Today, what we want to do is basically to complete the work example that we started last week. And to start another bit more, I would say, extensive work example that I sent you yesterday, or the day before yesterday, I can't remember now, which is a work example of a whole roof design. So this is a work example about one beam design, one member, and then we are going to move towards a work example of a whole roof design, just to have an idea of how to assess the load and what kind of verifications to do. Now, if you remember, last time we started by doing a preliminary design of our beam. We said that we have a long beam, about 22 meters, if I remember well. It would be made of glue laminated timber. Of course, when you talk about a 22-meter long structure beam, of course, solid timber or solid timber is not a possible solution because you can't really find a tree which is. I mean, you can also find trees which are 100 meters high. You know, the sequoia trees in Canada. Of course, you can't really use it for a structural purpose because it's a trapezoidal shape anyway, so you cannot use. The only way when you exceed a certain length, I would say, nowadays when you exceed probably 5 to 6 meters, the only way is to use wood, engineered wood product. So either LBL, laminated in lumber, or glue laminated timber. So in this case, of course, we decided to use a glue laminated timber, and the result of the preliminary design is a beam which is 18 centimeter wide and 1.5 meter high, more or less. So it's quite a big beam, I would say. So what we did last time, we calculated the set weight. You remember how did we select the density? Because this was the only tricky thing, as I told you last time. How did you select the density, or let's say the unit weight, to be more specific, in order to calculate the set weight? If you remember, there are two ways. One way is to look into the table given by the national regulation. So this one, timber, so conifer and poplars from 4 to 6. And of course you take, if you don't know, you just take the average, so 5. If you want to be a bit more precise, what you can do, you can go into the table about glue laminated section, glue laminated properties. And from this table you have two value of densities. So the characteristic value, the mean value. So you have to select one strength class. For example, in this case we selected the GL28H. Do you remember what does GL28VH mean? So GL means what? Glue laminated. 28. Which strength? Because you said it's several strength. Not like for concrete. Concrete is always compression strength. In this case, for timber, what is this 28? Daily characteristic strength. Okay? And then this H, what does it mean? Homogeneous. Because the ruler may be homogeneous, or, which is the other option, you remember yourself? Combined. Which means combined means that you put in the homogeneous section, we use boards all of the same strength. Okay? So all the cross sections made from boards which are the same strength. Instead, in a combined version of Lula, we put the best strength boards outside and let's say the worst one inside. Okay? That's the difference. Okay, so in this case you should select one class, for example GL28H, and then you have two values here. The characteristic value of density and the mean value of density. Which one should we use for assessing the set weight? Okay, remember, the mean value is used to assess the set weight. Because you may recall 2 or 1 year ago when you attended my course, I told you that when we talk about self-weight, it's true that in the regulation you find GK, which strictly speaking means characteristic value of the load. And the characteristic value of the load the load should be, remember, which fractile? Is the lower fractile, the mean, or the upper fractile? The upper fractile. So when we talk about actions, GK means the characteristic value of the load, and this could be the upper 5th percentile fractile, or if you want, the 95th lower fractile of percentile, okay? However, we said that for permanent loads, since the coefficient of variation, so the standard deviation is very small, usually the regulation refers to the mean value. So you find it written GK, but actually, strictly speaking, this should be a GM. It should be the mean value of the permanent loads, okay? Just not to make any confusion, because all the other loads are QK. The regulation says, okay, well, I put the GK, but just keep in mind that those are the mean values, not the characteristic one, okay? And then, of course, instead they apply a smaller gamma G coefficient like 1.1, 1.2, they apply a higher value, so 1.35. Okay? So it's 1.35 times GK, but this GK is a GM. So in this case, we have to keep in mind we have to use the mean density. Okay, it's clear? Then we will see later on that the characteristic value of the density will be used to find some other properties. For example, the embedding strength of timber. The embedding strength of timber is what we are going to use when we are going to calculate the strength of a connection. For example, of a dowel connection, of a bolted connection. Okay? Good, so going back, what we did, we calculated the set weight. So set weight of a beam, we just remember at the end, like I told you during the structural design course, we are designing a beam and we need to find out the uniformly distributed load, which is expressed in a force per meter, force per length, force per unit length. So the unit of measure kilonewton per meter. In order to get kilonewton per meter, we multiply the density or specific weight, 500, times the cross section of the beam. This 100 that you find here is just as a matter of conversion, because we want to convert. This is kilogram per cubic meter, this one is centimeter, this one is centimeter. We need to be consistent if you want to find kilonewton per meter, otherwise we get something of different. Okay, so be careful, of course, when you do this calculation. It's easy to get wrong with the units of measure. So everything is simple here, we need to be careful about the units of measure. That must be consistent in order not to get wrong results. Okay? Then the permanent load, we had a surface, a pressure, 7 kilonewton per square meter, which is the permanent load above the beam. And this one we multiply by the tributary width, which is the spacing between the beams, 7 meters. Then we sum the two permanent loads. You see GK1 plus GK2, which is actually, we said before, would be a mean value, this one. And we get 4.98 kilonewton per meter. And then we calculated the snow load. Snow load was already given, 1.28 kilonewton per square meter. Again, we need to multiply by the tributary width, so the spacing between the beams. So 8.96 kilonewton per meter. Just as a small consideration, look at here at the incidence of the self-weight of the beam over the whole weight. It's 1.30 against 5. So 1.3 out of 5. So as you can see, it's true that timber structure are lightweight. In fact, you see, if you compare the self-weight of the whole structure with the snow load, which is the actual variable load, so you could say that the roof is built, of course, to resist to itself, but mostly to resist to the snow, otherwise we wouldn't need any roof. So you see that the self-weight 5 out of 9. So self-weight of the timber structure is about 50%, well, a little bit more, like 60% of the live load. You remember more or less how was this percentage for your floor, reinforced concrete floor that you designed a couple of years ago? So what was the variable load and what was the self-weight, more or less, just to have an idea? Yes, the question is, when you designed the reinforced concrete structure 2 or 1 year ago, depending on when you attended the course, you designed a reinforced concrete floor which had a certain permanent load, and this floor was designed to resist a certain live load. So what was the ratio between the two? So what was the self-weight of your floor, reinforced concrete floor or roof, whatever you want, as related to the live load? For example, let's start from the live load. What was the live load in your design, your reinforced concrete design? Yes, what was which number do you have? 2. So, exactly. So this was 2 kN per square meter. Of course, it is not immediately comparable because this is already multiplied by the tributary width. But in your case was 2 kN per square meter. This was the live load. And what was the self-weight of your floor in kN per square meter, more or less? Do you remember? 4, 5. I would say yes, more probably 5, 6, 4, 5, something like this. So the self-weight was more or less 2 to 3 times the live load, because the live load was 2. So let's say in your case, QK was 2 kN per square meter, and GK, also including the partition, I'm talking about everything, was, let's say, 5 to 6. If it was 6, it means that the permanent load was 3 times the live load. Okay? So in this case, as you can understand, I mean, the reinforced concrete structure, of course, is made to resist a certain live load, but the incidence, the percentage of the self-weight is very important. Because to resist 1 kN per square meter, you need to have 3 kN per square meter of self-weight. So 3 times the live load, more or less. In this case, to take 9, I need 5. So I need more or less, before I needed 3 times, here I need half, 0.5. So there is a huge difference of the 2 cases, as you can understand. That's why we said last time, or twice, I don't know, maybe some week ago, that timber structure lightweight. And if you remember, I also told you that if there is an exceptional snowfall, it's most likely that we might have some problem with timber, with a timber roof, rather than with a reinforced concrete roof, if you remember. Because with a reinforced concrete roof, itself, the permanent load is very high. Whilst that here, the permanent load is very low. If you remember, we did a small calculation to demonstrate this, because it's not so obvious. So as a matter of comparison, just this. I repeat again. Here we need more or less 50% of the live load is structural weight. While for reinforced concrete, we had that 300% of the live load was, or 200% was self-weight. So the ratio of 4 to 6. Okay? I can tell you that's very close, you could get to very close results if you have steel structures. So steel and timber, they are very compatible in this kind of ratio. So when you are going to attend a steel course, you will find more or less the same results in terms of lightweight. Okay, it's clear? Of course, another remark we could say is that if you get here a wrong value of the permanent, of the self-weight, it's not so important as if you get a wrong calculation of the self-weight for reinforced concrete. So for reinforced concrete, the self-weight is much more higher as a percentage of the whole ultimate load, load. Here it's less. Nevertheless, note that it's still important because we are talking about, you see, the self-weight is more or less 1/3 of the total, let's say 1/4 of the total permanent load. So also here we need to be a bit careful because you know this timber beam is quite big. Almost 1.5. It's big, which is almost as high as me and long 22 meters. So it's quite an important percentage. Okay. Good. So we've got now all the loads. Note that in this case, we are considering only two loads, permanent and life load, or snow in this case. You will see that strictly speaking there are other two loads that we should consider. In the next exercise talking about the roof, we are going to do the whole complete load assessment, and in addition to the snow, we are going to calculate also the maintenance and the wind. But I can tell you that in 90% of the cases, if we ignore earthquake, the snow load is by far the most important one when we talk about the roof. Now, we need to do now the load conditions. So we said before we have two permanent, self-weight permanent, GK1 and GK2, and we have one variable load. Now, if we were to design a reinforced concrete roof, how many load conditions would we have to consider? If this roof was made of reinforced concrete, how many load conditions would you consider? Which one is the most critical? One. Which one is one? Do you remember?
The ratio.
No, we're talking about now reinforced concrete. My question was, if this roof was made of reinforced concrete, how many load conditions would we have to consider? One. Which one was this load condition for, let's say, ultimate mistake?
With both of the load.
With both of the loads would be gamma J1 times gamma Jk times Jk plus gamma Q times Q. And that's it. Okay, no other problems. Clear? Okay, since now we are talking about timber, and I told you that if we have different loads in the same load condition for different loads, the strength also depends on the load condition, because the strength depends on the load duration class via the K mod factor. And of course, if you have two loads in the same condition, you need to take, you have two values of K mod. You need to take, remember, the maximum value of the minimum value of the K mod. You have to take the maximum, okay? Meaning that it's not sure that the most critical load condition will be the full one. So gamma Jk plus gamma Qk may not be the most critical because the K mod is the maximum one. So it's the maximum load, the maximum strength. So we need also to check that the other load condition, the one without the variable load, which is only permanent and has a K mod lower, we need to check the other one because the other one may be more critical. For the simple reason that the other load condition is smaller, but also the strength is smaller, because also the K mod is smaller. So we don't know a priori which one is the most critical one. Well, strictly speaking, instead I told you a small trick actually to find out which one is the most critical, if you remember, without having then to solve all the beams and do all the verification. You remember the trick? What we have to do is the combination. So first of all, we need to calculate both values. So one value will be gamma J GK, gamma G GK plus gamma Q QK. This will give a certain value. Then we calculate gamma G GK, another value, and then we do the ratio between those two values separately and then associated K mod. Okay. The most critical load condition is the one where this ratio is maximum minimum. Maximum, okay? If you remember, for reinforced concrete, we take the maximum one. Also here we take the maximum one, but the maximum value of the ratio, okay? So this is what we have to do. So we calculate, we just remember gamma G. Now, this exercise is done considering the Euro code, so gamma G is 1.35. If you consider the Italian regulation, the gamma G will be 1.3. Then the other one, 1.35 GK plus 1.5 QK. So one is 6.7, the other one is 20.2. Which service class? Because you remember, K mod is also depending, does not only depend on the load duration class, but it also takes into account the moisture content. so the service class. Now we said that this one would be a kind of a workshop. And being a workshop, this is not always heated. Very often this is unheated. Okay? So basically our being will be in indoor condition because it's inside, but in unheated climate. If you look at the choice of the service classes, you will find that for indoor conditions and an unheated environment, the service class is number 2. Okay, service class 2. Now, we need to find out which kind of load we've got here. So we've got one permanent load, self-weight, more than 10 years. And then we've got the snow. For the snow, you see, snow may be 1 week to 6 months, medium term, or less than 1 week, short term. Usually, of course, this depends on the local conditions, but usually we say that above 1,000 meters, we consider, at least in our country, in Italy, we consider snow as a medium term, and below 1,000 meters, above sea level, we consider snow as a short term. In this case, we have assumed that we are below 1,000 meters, so the snow is here. Short term, so we have one load which is permanent and another one which is short term in terms of low duration classes. Now we go to this table, which is taken from Eurocode 5, also the Italian national regulation is a similar table. We select glue laminated timber. We select the line corresponding to service class 2, and then we go to select the two loads. We have a permanent one, so K mod is 0.6, and we have a short-term action, the snow, K mod is 0.9. And then we can do this ratio. So F1, only permanent, 6.7 divided by 0.6, 11.2 kilonewton per meter. Second one, F2 is 20.2 divided by 0.9 is 22.4. Meaning that, in this case, very clear that the second load condition is the most critical one. So let's say that the complete load condition, the one that we would have considered also for reinforced concrete design, this one is also in this case for timber the most critical one. So from now on, we only consider this load condition. We don't go back to consider also the other one, okay? From now on, all the checks, all the verification will be done considering only the second, the most critical load condition. Okay? Because it's clear that if this load condition is satisfied, also the other one will be satisfied because it's a lower ratio. Okay? Now what we have to do is we need to go back to what we studied, what we learned in statics. In this case it's very simple. We have a simply supported beam. We have a load condition of 2, which is a certain value. We need to solve externally our beam to find the external reactions. And then we need to resolve the beam internally to find the internal forces, so the shear force diagram and the bending moment diagram. So this is a very simple case. All of you probably know by heart the solution of this thing, not even needed to write the equation. We know that the restraint reaction is basically half of the resultant of the load, so F2 times L divided by 2, this is the restraint reaction, which gives us also the maximum shear over the support. The diagram here is linear, because as you remember, this diagram is the integral of the diagram of the load. Or if you want, the diagram of the load is the derivative, the first derivative of the diagram of the shear. And then we can calculate the bending moment diagram, which is a parabolic curve. The maximum is in the center of the beam. And the maximum value, you probably remember by heart, is, remember by heart the maximum bending moment. So Q, or in this case F2, times L, length square divided by 8. No, usual formula. So you can replace the symbols with numbers. So 20.2 kilonewton per meter times 22 meter divided by 2 is 222.2 kilonewton of restraint reaction. This is also, we said before, the maximum shear over the support. And then the maximum bending moment, 20.2 load times 22 squared divided by 8. So 1,222.5 kilonewton per meter. Okay? Okay, now if we were designing with reinforced concrete, what would you have done? Or what would you do now? Let's say, what would you do if you arrive to this point? You have to design with a reinforced concrete beam, like this. How would you follow up? Well, this we have already done, so you should know what to do.
Design for the maximum value of the moment.
Exactly. You will design first for the maximum bending moment. And what would you do specifically? You have the moment demand, which is 1,222.5, and then what would you do?
Calculate the area of the bars.
Yes. Well, yes, you have to calculate basically, well, the size of the reinforced concrete, so breadth, depth, and the area of the tensile reinforcement. Then if you need some ductility, you design the area of the compressor reinforcement. And in the end, what you do, after you do the cross-section, you need to calculate the bending moment capacity of this cross-section to compare it with this value here. So the bending moment capacity of your cross-section of your design shall be greater than or equal to this value here. Okay? This is what you would do now if you were using reinforced concrete. Since instead we are using timber, how we proceed? Remember what is the most important difference between reinforced concrete design and timber design at this stage here. Exactly. So for timber, if you remember well, unlike for reinforced concrete, unlike for steel, for timber, we got to check the maximum stress in the point. So we don't consider, like for reinforced concrete steel, the bending moment demand, and we compare with the bending moment capacity, but we go back to what we used to do with the permissible stress method. So we go to compare the maximum stress in the most stress point of your volume. We compare this with the design strength of the timber at the local level. Okay? Exactly that we were used to do it in mechanics of structure. So mechanical structure, once you got to this point, what did you use to do it? Using the permissible stress method. What was the next step after that? We're talking about mechanical structure, scienza delle costruzioni. So, how do you follow up after here?
Find the value of shear.
Yes, but this is the shear. This is the shear. This is the
Down.
Yes.
The value down.
Yes.
And for the moment, they will be walking down.
Exactly. So for the bending moment, at that time, you were given a cross section, usually a complex cross section, never a rectangle, always something strange. But you were given the cross section. You were asked to calculate the maximum stress in the most stress point of your cross section, and then to compare with the permissible stress. In this case, we have a simple cross section, the rectangle one. But we don't have yet the size. Actually, we have a size, but it's a preliminary size. You know, this is 18 by what was 1.5 meter. This is a preliminary size. So if you have an Excel spreadsheet, you can also say, okay, I'm going to do the check on this preliminary size. I'm going to calculate the stress, the most stress point, so the outermost fiber, to compare this stress with the strength. And then, if the verification is satisfied, is more or less on the limit, okay, I finished. If instead it's not satisfied, I need to do a loop, I need to increase the depth or the breadth, and to do again the check until I got a difference which is smaller. You may also have that the verification is too satisfied. So, for example, you have a maximum stress of, I don't know, 100, and the strength is 60. So you are oversizing too much your cross-section, then you need to reduce it a little bit. Okay, so you can also do, if you do an Excel spreadsheet, you can do a loop very simple, because you change the value, automatically you get this verification, these two numbers, so the strength and the strength capacity, the strength demand, which are changed automatically. You can also do this way. Otherwise, if you are not using Excel, but you are working by hand, for example, like you will have to do it during the exam, or like they used to do in the past, what is the best thing to do right now? Well, the problem is that we don't know yet the final cross-section. So we could try, since we have a simple cross-section, we could try to design the cross-section automatically in order to satisfy the verification, the design inequality. How can we do this? Let's go to C. We can invert the design inequality for flexor and algebraic mistake. So let's go to write down the design inequality. So sigma MYD, what does it mean? Sigma means stress. Okay, we're talking about stress, not bending moment. Stress, M means bending, Y means bending around the y-axis, which is the horizontal one. Okay, so we have the cross section, Y is the horizontal, is this one basically. And D is the design value of the stress, meaning the value of the stress in the most stress fiber due to the design value, which is the ultimate steady load. Okay? So this is MD. Here we use the formula, as you remember. Here we use the formula of Navier that you studied in mechanics of material. This will be sigma MYD. This is MD. So MD, bending moment, divided by section modulus. In Italian this is the modulo di resistenza. So section modulus around always Y. This must be less than or equal to FMYD. Again, F this time is the strength, and bending, Y around the y-axis, and the design strength. The design strength, if you look at the formula that we derived last week, is the product of three coefficients: system coefficient K times size coefficient KH times K mod times FMK. FMK is the characteristic bending strength of timber divided by gamma M, partial safety factor. Okay, now if you look at this design inequality, what are the unknowns in this design inequality? MD. Do we know MD when we arrive at the stage of the design? Yes, we just calculated before, because MD depends only on the external load. Okay? The only little problem is that in the external load is also the set weight, which depends on the cross section, okay, which we don't know yet. Okay, but MD we know. WY, section module. Do we know the section module of the cross section? No. Well, we know a first attempt of the section module. We know that the calculate the section modulus of the preliminary design that we calculate by engineering judgment. So strictly speaking, this we don't know because this was based on pure engineering judgment. Okay? So Wy is one unknown at this stage. Then Fnyd, K6, system coefficient. Do we know the system coefficient? Well, yes, because we know it's done our calculation. If you are doubts, you put K6 equal to 1. If you are in doubt. Anyway, we may between 1 and 1.1, 1.15, not important. Kh, size factor. Do we know size factor? Well, we don't know the size, but we know that above 600 millimeter, Kh is equal to 1. Now we're talking about a beam which is 1,500, so for sure it's above 600 millimeters, so we know also Kh will be 1. Do we know K mode? Yes, because it's related to the load condition. So K node is given, it's 0.9 in this case. Do we know F and K? Characteristic bending strength of Blueland? Strictly speaking, no, because we could choose among different Blueland classes. So when we write here, we need to make an assumption, like we were doing for reinforced concrete. For reinforced concrete, we were choosing a certain class. At that time, if you remember, there was a criterion to calculate the strength of reinforced, at least the first attempt of the compression strength. Do you remember which criterion we suggested for reinforced concrete to start with a certain class?
Considering only the vertical load?
No, there was a criterion that was based not on strength.
If the environment was aggressive or...
Exactly, it was more, this criterion that I gave it to you was based on the design for durability. So you are designing your beam for strength, but in order to calculate the minimum compressive strength, you could check the kind of environment where the structure was in, and to make, there was a table, if you remember, that was given to you the minimum value of compressive strength of concrete in order to make the concrete durable in that environment. Okay, so you had for reinforced concrete minimum. Here instead we don't have everything. It's just based on engineering judgment. Or you could say, okay, usually, for example, the GL28H is one of the most used strength classes for Blueland. So you use GL28H. Okay, you make an assumption at this point. Gamma M, do you have gamma M? Partial safety coefficient? Yes? Yes. Because this is given by the regulation, either the Eurocode or the Italian code. So in the end, you see, the only unknown is WY. But what is WY for a rectangular cross section? What is WY for a rectangular cross section? Remember the formula, the section modulus. D squared divided by 6. Yes, the elastic one is divided by 6. The plastic one is divided by 4. Which one do we use for timber? The elastic one or the plastic one? Are we sure that we use elastic? Elastic, no doubt, okay? Because if you remember, we said even though there is a small plasticization in compression, there will never be a complete plasticization like for steel. Never. So for this reason, in order to make it simpler, the regulation just ignore the plasticization in compression and just refer all the value of the bending strength to the case of purely elastic behavior. So always use here the elastic value, okay? Good, so in the end, how many unknowns do we have here in this design inequality altogether? Two unknowns. So two unknowns means that we have an infinite solution. So again, we need to make some assumption. If you are designing, for example, with a sawn timber, for a sawn timber, for a solid timber, usually the assumption was that B and D, B should be more or less 0.7 of D. in order to optimize this kind of behavior of the beam. This is for some timber, okay? So you have one relationship here, another relationship here, and then we can solve, we can get only one between, either B or D. For glulam, instead, this relationship is not valid anymore, because for glulam, if you remember, usually we have a very narrow cross-section, very high, like in our case. So for glulam, we need to make an assumption. For example, the breadth. We can decide in this case to keep the breadth to 18 centimeter and to calculate. So if you remember, the preliminary design we say 18 times 1.5. We keep the 18 and we calculate the right depth in order to satisfy the equality. Okay. So in other words, what we are doing, we isolate Wy from this design inequality, and we express Wy as a function of all the other quantities. So we replace all the symbols with a value. As usual, be careful about the conversion, because N is in kilonewton per meter. This one is megapascal, which means Newton per square millimeter. Meaning that here you need to multiply by 10 to the power of 6. You need to go from kilonewton per meter to Newton per millimeter. Okay? Kilonewton per meter, if you need to transform to Newton per millimeter, you need to multiply by 10 to the power of 6. And then in the end, you see, this is the minimum value of the section modulus of the cross section that we need to have in order to satisfy the ultimate limit state. Of course, we can achieve the same result using different shape of cross section. It could be a very narrow, can be bigger, and so on. We have infinite possibility. We need to fix, for example, a variable, for example, the breadth. Or the height. In this case, for example, here you see I use the same height and I calculate the breadth, 166. And we could say, okay, since in our preliminary design we started with a cross section that was 180 by 1 meter 48, this is more or less the same. So, also the other criteria, if you remember, that the breadth cannot be 166 millimeters. Nor can be 170 millimeters, because I told you that the breadth is 2 by 2 centimeters, so there is not a continuous variation. The breadth must be either 160 or 180. Since we got 166, the only possibility is 180. So this is a coincidence in the sense that the results of the design is exactly the same beam that we preliminary design before. But usually when you do this calculation, you will get something different. So you need to adjust either the depth or the breadth. Okay? And when we adjust either the depth or the breadth, we need to see whether it's necessary to reassess the self weight. If the difference is minimum, you can also ignore this increase in self weight. But if the difference is important, then you need to again to recalculate the self weight, to go back to recalculate the bending moment, and because of course if you change the set weight, also this one is going to change, and so this one is here, you need to increase a little bit also the section modulus. Usually only one iteration is needed, it's not needed hundreds of iterations, okay? So it's very simple. But I would say that nowadays the easiest way for you now, when we are going to do your design, the easiest way is to create an Excel spreadsheet to memorize all the formula. For example, this formula here is quite trivial compared to the formula that you were used to memorizing in reinforced concrete design. And then you can very simply, by changing the number, find out immediately the optimal result. Okay? Any questions about what? Yes?
There is another unknown parameter that is KH, because
Yes.
in preliminary design you can use the KH relative to the first section.
This one.
But now that WY depends from KH,
Yes.
I
Yeah, you should change. You should update also the KH. But in this case, we don't need to do anything because you see this KH is greater than 1 only below 600 millimeter depth. Since we are 1.6, 1.5, we are far away. Of course, if you were close to 600 or lower than 600, then you should also update this.
But normally not increase very much. Okay.
No, it's between 1 and 1.1. So the best thing is to start with 1 and then you see if you need to change it. Sometimes you actually just ignore it because it's just 10% more, it's not a lot. But of course, if you organize everything in Excel spreadsheet, it's very simple because you memorize in Excel spreadsheet also this formula with an if. Everything is going to be updated automatically. Okay? I would say that nowadays, really, a simple way now, you know, this kind of thing is what you used to do in the past when you did for the exam, when you can use the computer. But nowadays with the computer, it's very simple to memorize all the formula and then you very quickly to check. Of course, in the Excel spreadsheet, as you know, you need to spend lots of time the first time to memorize all the formulas because you need to check if the formulas are right or wrong. But then, of course, doing the design becomes very fast, very easy. So my recommendation would be definitely to develop an Excel spreadsheet also here. Also because the formulas are not very complex. And you should be an expert now after, you know, reinforced concrete design in case of Excel spreadsheet, right? Okay.
So, in this case, we use the value of find the value.
Yes, you can.
Is the same when we check the value of the.
Of course, yes. You can choose what you want. You have two unknowns, so one of the two must be fixed in order to find the other one. If we were with some timber, then we would take this relationship here. But since we are with ruler, we can't do it. And just remember again that the cross section in the end, you cannot have a continuous variation of your ruler cross section because just what I'm saying, you could also have a cross section which is wide 166 millimeter. So in order to do so, the producer would basically produce a beam which would be 180 by 1480. And then it would cut down this 12 millimeter in order to get 166. So in the end, this will result in an optimized design in terms of volume material. But your cross section would cost more. Because it would also charge you for having to cut your beam. Exactly. Okay? So remember, always follow, it's more or less like for steel. You can have an IPE 143. The idea is either 140 or 160. Nothing between. And similar here for timber. For timber it's easier to have something between, but it's more expensive. Because they have to start from a bigger cross section and then you have to cut it. Okay, it's clear? So remember that commercial cross section are increased by 2 centimeters in width and 4 centimeters in depth. So this is the kind of range of value, commercial value that you find around. In Italy, but I would say all across Europe. Other questions? Yes?
What is the height of our ruler?
The height you can get up to 2 meters.
I mean depth.
Yeah, the depth. Yeah, the depth is up to 2 meters. Yes. Yes. Usually you could also have more than 2, but usually 2 is the limit in terms of depth. If you have to go higher, it's probably better to use crossland. Because with crossland you can get up to 3 and more than 3 meters high. But in that case, the length for crossland usually you get up to 18 meters. So 22 is not so. I mean, there are few presses around, even not sure where they are, to make a beam long 22 meters out of crossland. It would be a bit more challenging. Other doubts? Okay, so this is the reference table here. If you remember, there is also another reference table for combined ruler that I gave you before. We were talking about engineering products. This is the table of the safety coefficients from the Eurocode, so 1 to 25 for ruler and timber. Just a reminder that if you design in Italy, you need to use the safety coefficient given by the national regulation for construction. This 1.25 becomes 1.45. Okay, so 1.45 in Italy. Okay, so now we design our beam. So we'll say 1,480 millimeter depth, deep by 180 millimeter width. Of course, since this is the result of the design, we don't need to check again the design inequality, because we've inverted the design inequality in order to find this dimension and to be sure that the design inequality is satisfied. So we don't need now to do again the design inequality, to check the design inequality and add a mistake. It's just a waste of time. Because unless we made something wrong in our calculation, this is automatically the sizes of the beam that are going to comply with the design inequality. It's clear this? Because we have inverted the design inequality, so we don't need to go back to check. Good. So if you do something like this in the exam, you will be penalized because you have lost time for nothing, basically. Okay, it's clear. It's not that they say, no, you should give me something more because this something. No, it's wrong. You're conceptually wrong because you have already designed to make the design inequality satisfied. So there is no reason why you have to check it again. Okay. Good. So what do we need to do now? So what kind of other verification do we need to do in our beam? So we design for bending. So what do you think? What other verification do we have to do to complete our design? So we need to do the serviceability limit states, which means 2 checks for deflections, spontaneous deflections and final or long-term deflections. What else? This is a serviceability limit state. What else? What are we still missing to complete the design? Okay, which are the adamant mistakes? Shear of the supports. Okay, so bearing, so compression perpendicular to the grain over the supports. And buckling, lateral torsional buckling of the beam. So we have 3 ultimate mistakes to check and let's say 2 serviceability mistakes. Now, what is the best way, the best order to proceed? If you have an Excel spreadsheet, of course, everything is done at the same time. So all the formula memorized, so you can check it. Once you input the size, for example, 180 milliliter by 1,480, immediately you can see if all the checks are satisfied or not. So in this case, no problem. They are all done. But instead, if you have to do by hand, or if you have to do this in the exam, for example, usually this is one question for your exam to design a beam. So if you have to do by hand or in the exam, what is the best way to proceed? Well, particularly when you have very long beams, usually serviceability state it's quite complex. I mean, it's usually maybe the Governing design equation, serviceability state, and the second one, that will be critical, is lateral torsional buckling, as you will see at the end of this presentation. So the suggestion is to, after designing your beam for bending, to go to check immediately either the lateral torsional buckling, if your beam is long and you don't have the strength, okay, across, or serviceability strength. Those are the 2 to proceed with. Okay? In this case, for example, we decided to go for the serviceability states. So we have 2 checks, if you remember we saw last time. If you do design according to the national regulation said that we have to calculate the instantaneous deflection under the variable part of the frequent serviceability limit state, FC prime, and the final net deflection under the frequent load combination, both values shall be checked against some limits given by the regulation. Given by the regulation for steel. And we said that the same limits for the steel can also be used for timber. So, Fc prime in our case should be QK1, so the basic variable action plus the combination values of all the other variable actions. In our case, we have only one variable action, and with the stone, so we have only QK here. And the value is 8.96 kilonewton per meter. FC, the total frequent load combination, is GK plus QK, because we don't have other QK. So, 13.94 kilonewton per meter. So, if you look at the formula that we derived last time, it was last week, the instantaneous deflection due to a certain load, Fc prime, you remember, unlike what we were used to do it for reinforced concrete, or for steel, actually for steel we haven't done anything so far, we'll do it probably next year, you need to remember that also the shear component of the deflection is important. So we need to add the shear component of the deflection to the bending component of the deflection, that one that you are used to consider again in structural mechanics. So the bending component of the deflection, in this case it's a uniformly distributed load on a simple supported beam, 5 divided by 384 times QK, because Fc prime we said is only QK in this case, times L to the power of 4 divided by the flexural stiffness, E, Young modulus of timber parallel to the grain, and Iy, second moment of area of the cross section around the y-axis, plus the shear component of the deflection, 1.2 for a rectangular cross section divided by G, shear modulus, times A, area, times QK times L squared divided by A. And this one shall be compared with a limit given by the regulation. So we will see later, it is a table, actually you can see immediately, then we go back. So this is the table taken from the Italian regulation for construction. See the limit of flexibility. So for the vertical deflection, we have a difference between roofs and accessible roofs. So for roofs, if a roof is not accessible, then the instantaneous deflection shall be less than 1 divided by 250 times the length. Instead, if the roof is accessible, this instantaneous deflection will be less than 1 divided by 300 times the span length. In terms of net final deflection, is 1 to 100 or 1 to 150, depending on whether the roof is not accessible or it is accessible. Okay? So in our case, of course, this is the first line, the one that is important for us. Okay, so instantaneous deflection, where we sum the two components, the bending component of deflection, the shear component of deflection, shall be less than or equal to 1 to 150th of the length. Final deflection, how do we calculate the final deflection? If you go to see this equation that we derived last time, you will find that there is a first component associated with the permanent load, so the instantaneous deflection due to the permanent load, times 1 plus K def, where K def, if you remember, is the creep coefficient of timber, plus the instantaneous deflection due to the variable load, multiplied by 1 plus psi 2 times K def. So for the variable load, we need to reduce the K def by multiplying it by psi 2, which is this combination coefficient used to assess the quasi-permanent load condition. So if you remember, we said that in order to calculate the long-term deflection, we need to multiply the instantaneous deflection times 1 plus the k depth, creep coefficient. But this is true only for the quasi-permanent load condition. If you have a variable action, you need to consider that only one part of the variable action is quasi-permanent. So for example, for a room like this, only 30% of the variable load is considered as quasi-permanent. Okay? The other 70% is considered as a frequent load combination, not as a quasi-permanent. So for this reason, this is cited here. Okay? How do we calculate the instantaneous deflection due to Jk? Exactly like the formula that we saw before. So again, we have the sum of the bending component of deflection plus the shear component of deflection. But in this case, of course, the Qk was replaced by Jk. And of course, here again, the same as above here. Okay? This should be less than or equal to L divided by 200. Okay, any doubts about this? If you look at the lecture that we went through together last week, you will find all these formulas. Okay, now let's do me some questions. Now we need to put some numbers inside here. So L is known, GK is known. E, which value of the Young modulus of timber do we need to put there? Since we have 4 values, if you look at the table, we have 4 values of Young module of timber. We have Young module of timber parallel to the grain mean value, Young module of timber parallel to the grain characteristic value, then we have a shear modulus, and then we have mean value shear modulus, and then we have Young module of timber perpendicular to the grain. So which value of E should we put inside out of these 4? The mean value of which one? Parallel to the grain, perpendicular to the grain? Parallel to the grain. So the mean value of Young modulus of timber parallel to the grain. Okay, this is what we need to put inside the formula here. Then we have the shear modulus of timber, mean value, put inside. Iy, second moment of area of this cross section. Can you tell me the formula of Iy for a rectangular cross section? Second moment of area of a rectangular cross section around Y is B D Q divided by 12. Right? So, modes of elasticity for GL28H is 12,600 megapascal, so Newton per square millimeter. Then the shear modulus, also here we need to use the mean value, which is, you see, 650 megapascal again, so Newton per square millimeter. Value of the coefficient psi 2, you see, for office buildings would be 0.3. For snow below 1,000 meters above sea level is 0. Meaning that for snow, we don't consider any creep effect in the end. So if we have a snow as the only variable load, basically the whole snow is considered as a frequent load combination and nothing as a quasi-permanent. Value of Kdef is the creep coefficient. Glue-laminated timber, 7 class 2, value 0.8. So, we calculate now the second moment of area. This you see is millimeter to the power of 4. The area is this value here. Instantaneous deflection, if you put all these numbers within the formula, and again you need to be careful about the conversion. You see in this formula here, this 8.96 are kilonewton per meter. 22, what was this 22 here? The length, which was expressed into millimeter, so 23 meter times 10 to the power of 3. Everything here was expressed in millimeter, and then you need to multiply, well, this is basically megapascal, so newton per square millimeter, and this one is millimeter to the power of 4. So in the end, you find your deflection in millimeter. 44.6 plus 3.7, so 48.3. The limit is 1/50th of the length, so 88 millimeters. So we see that the first verification is satisfied. As a comment, let's have a look to the influence of the shear component of deflection. Is it very important in this case? No. You see, it's 4 millimeters out of 44. Basically, it counts as 10%. Why is it not so important in this case, in your opinion? Because the beam is very low. Okay, because the beam is very low. Like we demonstrated last time, it was also told you by the colleagues from mechanical structures. The shear deflection is very important, may be very important when you have a short span beam, not when you have a very long span beam. Okay, now we want to calculate the long-term deflection, so the final deflection, but again we put all the numbers inside. And in the end, you see, we find out that, as we already observed before, the snow load doesn't have any creep contribution, because here you find, you see, this creep contribution is 0, not because the creep coefficient is 0, but because the side 2 coefficient is 0. So here we don't have any creep coefficient, any creep contribution. And in the end, you see that we have 96.7 millimeters as a final deflection. 96.7 millimeters must be compared with 1/200th of the length, which is 110 millimeters. So also the second verification is satisfied. As you can see here, the safety margin is much lower than before. Because in this case, we have 97 against 110, so we are quite close anyway. So you can see that this, particularly the second, the final deflection, may be easily the governing design criterion. In this case, it's not actually. But for example, if you had the same beam to be designed as a floor, in this case, this would reduce to L over 250, so this one would go basically below this number. So we would have then to redesign the beam in order to satisfy this limit state. Of course, if you need to redesign the beam, suppose that this verification here was not satisfied. Suppose that now the limit was L over 250. Can you make this calculation for me? L divided by 250, so 22 divided by 250. Actually, no, sorry. It's already that. Where was it? This one. This. So it's 88 millimeters. So 88 millimeters. Suppose that we had to design in the long term for this criteria. So we will get here 96.7 millimeter, which would be greater than 88 millimeter. Okay? What do we need to do now, arrive to this stage? What would you do? If we were designing a beam for example, a roof which was accessible, and then the limit was 88 millimeter rather than 110, what would you do? Or suppose that your final exam, and you get to this point, then your design for them, then you get here, you get 96.7, which is greater than 88 millimeter. What do you have to do now?
Change the cross section.
How would you change it?
We can use the second moment.
What does it mean, the second moment?
The value of B or H.
Yes, we have to change either B or H. Either B or H. So, for example, what can you do? You could also do another thing actually. You could also go to invert this design inequality in order to get the sizes. But this is a bit complex because you see you have the sizing into I here and into A there. So it's I mean, if you have an Excel spreadsheet, it's only a matter of changing, the number to see. Probably in this case, since we are quite close, what could be the easiest way to do? What would you increase? The breadth or the depth? You can actually increase both of them. So if you increase the breadth, which breadth would you take? We said that the breadth can only be increased by 2 centimeters. So now we have 18 centimeters. We could try with 20 centimeters, for example. This could be one possibility. Or, if you want to increase the depth, you could say we should move back from, what was the depth here, from 1,480 to 1,512, exactly. So either solution would be fine. So you change it, then you recalculate everything here, and you see if after this recalculation the verification is satisfied. Then you need to think about if I increase by 4 centimeters the depth, or if I increase by 2 centimeters the breadth. Is it very important then to go to change also the set way? Of course, if you have an Excel spreadsheet, everything is done automatically, so it's not a problem. If you are in a final exam, what would you do? You have 3 hours, so you don't have time to lose too much.
Si è verificata perché la verifica, cioè se è riuscita la verifica precedente non serve, perché abbiamo una dimensione maggiore.
No, what I'm talking about if you need to recalculate the set way. In this case, you are increasing either the depth by 4 centimeters, so from let's say 148 centimeters to 152, or the breadth by from 18 to 22. Or to 20, so no, we said from 18 to 20. Are you going to recalculate the set weight again? No, you write down that there is an increase, small increase in set weight. And then of course when you do the verification you need to make sure that you have a little bit of margin. So for example, if you suppose that from here you change the breadth and then you get, instead of 88 millimeter, instead of 96.7 millimeter, you get 88 millimeter, which is equal to 88 millimeter. Okay? In this case, is it are you satisfied if you haven't increased the set weight? No, because you are on the limit, unfortunately. So it's clear that in this case, even if you increase the set weight a little bit, this would translate into 89 millimeters, for example. Which, I mean, in terms of engineering, if you talk about the engineering point of view, to me, 89 millimeter or 88 is exactly the same, because there are so many uncertainties in calculating the creep coefficient, the modules that really is there. But of course, since after you have to enter this report to an authority, you need to be careful. So you need to avoid this kind of verification which are not, which are substantially satisfied but formally are not satisfied. So avoid, so in this case it would be better to reassess from the set weight and to increase a little bit more the breadth. So if you increase, for example, the breadth to 18 to 20, it would be a good idea to increase the 20 to 22, and then you are sure. Even if you don't calculate the same way again with 22, everything is fine. Okay? It's clear here? Any doubt? Because this could happen in the exam. Could happen that this one is more critical than the other one. So once you get to this point, you need to know what to do it without losing too much time. Okay, the second question for you now is this one. After that you change your cross section from, for example, 180 to 200 by 1480, and this verification here is satisfied. Not in this way, but like, for example, 92 greater than 88. So you don't need to calculate again the same way. Are you going to check again the bending strength for arithmetic mistake, since you have changed everything? No, why not?
You are increasing the...
You have increased the cross section, meaning that except for this little increase in set weight, which is negligible, how would it be now the verification at arithmetic mistake? Would be even more satisfied than before. So again, like I told you before, if you do it again in the exam, this choice will not be appreciated by you because it's loss of time. Okay? Since you are going to increase the cross section, there is no point to go to check again the flexible strength design that you already done before. It was already satisfied with the smaller cross section. It's clear to everyone this. Because this is a matter also of optimizing your time and knowing what you are doing. It's not a matter of mechanically just do something, okay? Any doubt about this?
At the exam, we can use a program to...
No, the exam not accept spreadsheet. You just use a more calculator. Yes, more calculator. But like for retrospective design, all the formula will begin. For example, all this formula here is somewhere will begin. Okay? So there is nothing to know here, except the concepts. Okay? Okay, now we move to the other ultimate limit states. We move to the ultimate limit state of shear now. Even though I can tell you the shear, it's, shear could be again critical if you have very tall and narrow timber beams like this, but on a short span. This case is usually critical shear. Okay, also here we need to check it under the most critical load condition, the one that we already found before, so 20.2 Newton per meter, all the same. Like we said before, we need to go to calculate the maximum shear stress using the formula, Jurasky formula that you learned in structural mechanics. So you know that there is a parabolic distribution of shear stresses around the depth. The maximum shear is on the neutral axis above the support, where we have also the maximum shear force. And the formula is here, it's 3 divided by 2, so 1.5 times the design shear divided by the cross section. The cross section, as you can see, is not B times H or B times D, like I noted that, but it's a B if, so effective width times H. So this B effective is a reduced width, taking into account that the glulam beam may have a crack. A crack that may reduce, may increase actually the value of the shear stress here. So this reduced breadth is calculated by multiplying the actual breadth by this KCR, which is set by the regulation to 2/3 formula. That's on timber. We already saw this last week, if you remember. So we replace again all the formula with the numbers. we get that the maximum design shear stress is 1.7 megapascal. The strength, K system times K mod times FVK divided by gamma n. K6, K mod and gamma n are always the same. FVK is the characteristic strength or longitudinal shear. Characteristic strength for longitudinal shear you can find from here. Shear strength, shear and torsion. Remember that for this verification you need to use shear strength, shear and torsion, not rolling shear. Rolling shear is for another phenomenon. Rolling shear is used for when you design panels made of wood. So plywood or cross-laminated panel, not for this design. Okay? We go back. You see that the verification size is 1.9 against 2.5. Also here, there is not a lot of margin, but anyway, the verification is satisfying. Other ultimate limitation to check is an ultimate limitation of bearing. So compression perpendicular to the grain over the support. In this case, we need to design the length of the support. So the length of the bearing surface, in order to make sure that we won't get failure or compression perpendicular to the grain over the support itself. The verification is sigma C90D, so stress and compression 90 perpendicular to the grain over the support due to the ultimate limit design load shall not exceed the design strength perpendicular to the grain with compression times this factor KC90. Sigma C90D is calculated by dividing basically the force perpendicular to the grain, so the restraint reaction, by the bearing surface, effective bearing surface, which is the breadth of the beam times the effective width. The effective width, as you can see, is equal to the actual bearing surface with an increase of certain amount. Now we're going to see 30 millimeter or 60 millimeter, depending on how the beam is done. The strength, FC90D, again, is calculated with the normal formula. So, you see the effective contact length parallel to the grain, so the verification is done, considering the formula what is called an effective contact length parallel to the grain, where the actual contact length L, so L is the actual contact length, our unknown in this case, because we don't yet know this value. At each side is increased by 30 millimeter, but not more than A. What is A? A is, you see, if the beam has an overhang on the opposite side, so on this side we can go up to A. In our case, for example, if A is equal to 0, it means that we cannot increase by 30 millimeter on the left because there is no overhang. While instead on the right, if the beam is continuous, we can go up to L, so no more than L, or L1 divided by 2, where L1 divided by 2 is the distance between the support and the first load. So this is our situation. So since we don't have here any overhang, A is equal to 0. So in our case, LEF would be the actual length here, which is unknown, plus 30 millimeter. KC90 should be taken as 1 unless the conditions of the following paragraphs apply. So in our case, let's see. So we are in this case here, members of discrete supports loaded by distributed load, not by concentrated load further than from the further away from the support than A1 equal to 2H. Case C90 should be taken as 1.5. In our case should be 1.75 for blue laminated soft to timber, provided that L is less than 400 millimeter. In our case, you see, this concentrated load should be further away from the support than L1 equal to 2H. So this is H, in our case almost 1.5 meter. So we could consider this 1.75 value only if the first load is further away from the support of a distance equal to twice the depth. But the depth is 1.5 meters, so the first load should be at least 3 meters away, which is a lot if you think about it. Also consider the fact that above this blue line there will be the purlins, there will be the church, the beams. So for sure there will be one beam here. Meaning that in our case, we cannot take this coefficient equal to 1.75 because, again, as I said before, L1 in our case would be 3 meters, and instead in our case L1 will be for sure less because we will have a first purlin, so first beam above here, in order to resist the load of the roof, to have the flooring of the roof above. Okay? So in our case, basically, KC90 is equal to 1. So in the end, we have this design inequality where we know everything but F. So we know LD2, which is the restraining reaction. We calculated it before. We know the breadth, 180 millimeter. We know KC90 is 1, K6 is 1, K mod is 0.9. And then FC90K, we can find this from the table, and gamma F is 1.25. So in the end, we can invert this design inequality. So we can explicitate L plus 30, which will have to be greater than all this kind of thing. If we substitute all these variables with the numbers, we find 686 minus 30. So the supporting length must be at least 656 millimeters. So 65 centimeters. In order to get the compression perpendicular to the support ultimately state satisfied, the supporting length must be at least 66 centimeters, which is quite a lot. From the table here, you can get that this FC90GK, which is the unknown, which is the property, the mechanical resistance, perpendicular to the grain, for all classes. And now we can ask ourselves, is there a way to reduce this supporting length from 66 centimeters to a lower value? Because 66 is quite a lot. It means that this beam must be supported by a column which is at least 66 millimeters wide. May also be enough. I mean, it depends what you have underneath. But of course, if you are supporting this Lulan beam by a column, the column would also be a 66 centimeter by 18 centimeter. However, if you are supporting the Lulan beam by a reinforced concrete column, you may want to avoid to have a reinforced concrete column 66 centimeter wide, because it's quite big. So you may have a smaller reinforced concrete column, and then you can ask we could ask ourselves if there is a way to reduce the supporting area. There is a way by using self-draining screws, quindi viti autoperforanti. So this is the idea behind here. If you put some self-draining screws, those screws can in some way help transfer the load here, that is the extreme reaction, from the outer fiber till the inner fiber of the wood. So basically, if you want this acts as a reinforcement, like a reinforcement in a reinforced concrete, which is going to transfer by bond, by friction, if you want, the load from this surface to the inner surface, the inner body of the wood. So, suppose that for design reason, we want to have a bearing length not greater than 180 millimeters. So instead that what was 600 and more centimeters, we want to limit the bearing length to 180 millimeters. So we need to have some screws. Let's say, for example, 2 screws here. It will be more than 2, it will be at least 4, because we are over 180 millimeter thread. So you will have at least 4 screws that will be installed. You see a 50 millimeter, for example, from the edge, and 50 millimeter from the end of this plate. And we will have to calculate how long those screws need to be in order to transfer the restraint reaction inside the beam and make it compatible with the strength perpendicular to the grain inside of the timber beam. So there is a very simple design criterion based on assuming that due to the bond between the screws and the wood, this pressure that we have applied on this bearing area will be diffused inside the wood along this 45 degrees inclined line. Okay, so we consider basically a diffusion of the load over this 45 degrees inclined line. So in other words, what we assume is that if this is the, suppose for example we have an inner support, so this is our beam and this is an inner support here, and here we put some screws. So the idea is that this pressure here, which is acting on this, let's say this steel plate here, thanks to the contact between the steel plate and the head of the screws, and thanks to the friction, the bond between the screws and the wood, there will be a diffusion of this load along this 45 degrees inclined line. So the idea is that as we go inside the wood, the stresses reduces. So basically, the stress reduces because increase this bearing length here that we consider when we calculate the sigma. So at this level here, the sigma 1, sigma 2, and sigma 3. We can write that sigma 1 times B1. So sigma 1 times B1 will be equal to sigma 2 times B2 equal to sigma 3 times B3. So this is B1, this is B2, and this is B3. So we consider the resultant constant at the different depths of the beam, but as we go inside here, we can consider a wider breadth over which to calculate the stress. And this breadth of this length here, this bearing length, depends on those two lines which are considered inclined by 45 degrees. Okay, it's clear the concept. So
NB is evaluated from the point, from the contact point to support and beam, or
from here, from where there is the convention, is where there is the first screw. Of course, this case is slightly different from this, because here we are missing one side. So here, strictly speaking, we have a 45 degrees going up here, and then it stays constant. Maybe I should have added a small line. I do now to make it clear. So you see in this case we have one line going up in this way, 45 degrees, the other one goes up 45, then here it cannot go any further because the thing is finished basically. So since our minimum distance in order to make the verification satisfied is 686, so in this verification we need to take outside the 30 millimeter of the effective width. So we need to take, if you go back, so this is the length that we need to find, 386. So from here, you see, we need to find out at which level of the beam we have a length of 686 millimeters. So 686 millimeters is where we have a distance here, you see LB, between this point of the screw. So since this is 45 degrees, LB is the same. So LB, so the minimum length of the screws shall be 686 minus 50. So basically this one, see this length here is 686 minus 50 minus 80, 556 millimeters. So basically the idea is that the screws are going to transfer all this restraint reaction within the wood, inside the wood, and they must be, they should be as long as the length needed in order to get at the end of the point of the screw this breadth here of 686 millimeters. Okay? I mean, it's quite simple. It's just a matter of, it's a kind of, if you want, geometrical relationship. You take up these two lines, 45 degrees on one side and the other, starting from the screws. You see what is the minimum length of the screws needed in order at the end of the point of the screw to get this line, which has the minimum length required to make the verification satisfactory. So 686 millimeter. Okay? In this case, we're only calculating the minimum length of the screws. Then, of course, we will have later on when we're going to understand how to calculate the strength of a screw connection. We'll be able also to make sure that those screws are sufficiently strong in order to transfer the whole load. Because if you think about it, suppose you put a very slender screw inside in order to transfer very huge load. What could happen? You have a very strong restraint reaction, you put only one very long but very small, very slender screw. What could happen if the load is too high and the screw is too small? So, what kind of failure could happen? Suppose you put a too small screw. A screw which is long, 556 millimeters. So what is needed from this? But there is only one and very small diameter. Yes. The screw could buckle inside the wood. It's like having a very slender pile in the soil. You have to transfer a certain value of load from the foundation to the soil. If you put one small pile too slender, this is going to buckle basically. It's going to buckle, it's going to break for flexural buckling. So same thing may happen here. Okay? So we have to do a check of these screws for flexural buckling. Considering the fact that in this case it's not like the Euler column that you studied in mechanics of material, because it's kind of an Euler column, it's a column subjected to a very strong compressive force, but there is nothing around. In this case, instead, there is around something. So there is the wood around, which in some way is going to provide some restraints against flexural buckling. However, you need to keep in mind that we have inserted a screw perpendicular to the grain. So perpendicular to the grain, this wood is quite weak and soft, because perpendicular to the grain, this wood is going to act like, let's say, some horizontal springs. But those springs are very soft, because the young modular of wood perpendicular to the grain, I remind you, is very low. So it provides some confinement, let's say some restraint against flexural buckling on the screw. So it's like having, let's say, a system like this. This is the screw, this is the node, and here you have some, it's like having a layer of Winkler spring, like you studied for ground, but these springs here are related to AD90, because this is perpendicular to the grain. The grain is in this direction, the grain of EP. So this is related to A90. A90, if you remember well, E90 is very low. It's 1/38 of the E0, which is 1/3 of the EC. So it's basically 1/90th of the young modulus complex. So very low. Meaning that these screws here cannot provide a very strong restraint against some kind of buckling inside. Okay? So those screws will have to be designed in order to satisfy flexural buckling, but not the normal flexural buckling as we studied for the column, because here there is a mean, there is a means, this wood which in some way is going to provide some restraint. But this restraint is very weak because the wood is perpendicular to the grain. Okay? So, by using 556 mm long reinforcement screws, the bearing length can be reduced down to 180 mm. Then what is still missing, diameter number of screws will have to be designed to resist the difference between the restraint reaction, 222.2 kN, the resistance of the wood, perpendicular to the ground, the bearing area 180 by 180. So in some way, you can assume that here the wood over this 180 mm is going to resist some compression perpendicular to the grain, but this compression perpendicular to the grain will be only one small part of this 222.2 kN, because it's related to the fact that we have only a maximum strength perpendicular to the grain of a certain value. So basically, the difference between the restraint reaction and the strength obtained by multiplying the compressive strength perpendicular to the grain by the bearing area, this difference will have to be resisted by the screws, which will have to be designed for flexible buckling, taking into consideration the wood parameter.